Hello, in this lecture, we will summarize what you've learned in about arithmetic for computers in our course of architecture and networks. So you know that saying about arithmetic, you will have addition, subtraction, multiply, and multiplication and division. And so here now we are going to the summary about binary addition. We will do in computer the binary addition. We do in the same way with what you did in what you do with decimal number. Here is an example. For example, you have a number of 7. You want to add with 6 in decimal. 7 is 0, 1, 1, 1 and 6 is 0, 1, 1, 0. So you add the first digit or the first bit 0 together. You have 1 plus 0 is 1 and you remember 0. This 0 will be taken here. It is 0 and so you have 0 plus 1 and the result is 0 here and you remember 1. This one will be taken here and so you have 3 bits of 1 here. Adding together you have the result of 1 here and remember 1. And this final bit of 1 will be taken here and add together with these 2 0 and so you have 1 here and the carry out will be 0 here. If you look into this value and you don't care about the negative or positive, I mean here will be a positive number. You will see that this value 1 1 0 1 equal to 13 and it is the result of 7 plus 6. And please remember that in this situation we consider this binary value is a positive value, so we don't care, we don't think about this value, this bit as a side bit, and this will be 13 in decimal. Now we go to binary subtraction. How can we do binary subtraction? Instead of doing subtraction, we will add the negation of the second operand with the first one, and the negate integer can be done by two complement, in which we will complement or invert the digit for that value and then we add 1 to it. Here is an example. For example, you have a value of 6 in decimal and you want to take minus 6 in binary. So 6 here in decimal will be 0, in binary will be 0 1 1 0. You make a complement or you invert it, you will have 1 0 0 1 and then you add with 1 and the result will be 1 plus 1 here is 0 and then remember 1, so 0 plus that remember 1 will be 1 and then these two bits will be 1 0 in the same way we did before, and so the result here is 1 0 1 0. It is minus 6 in decimal number. And here if you look into this bit, you can see that this is the side bit. It implies that this number, if you consider it as if you care about the value whether it is minus or plus, it will be a negative number equal to minus 6. Now we will do a subtraction. Here for example, you would like to do 7 in decimal minus 6 in decimal. Instead of doing minus 6, you will add with minus 6 here. That is the value of 1 0 1 0. So the second operand here will be 1 0 1 0 and here is 7 in binary 0 1 1 1. You do the addition. 1 plus 0 is 1 and remember 0. This 0 will be taken here and plus with 1 and plus with 1 you have 0 and remember 1 here. This one will be taken here And so this one plus with this one, you have plus with 0, you have 0 and you remember 1. This one will be taken here and plus with 0 and 1 here. You will have value of 0 here, and you have a carry out or remember the overflow of 1 here, as you use only 4 bits for storing your region. The region will be 0, 0, 0, 1, and this bit of 1 will be missing, and so 0, 0, 0, 1 will be 1 in decimal, and it is the region of 7 minus 6. And as I say, just say before, we have the overflow. The overflow in LACVS will be set to the flag, and in order to use the overflow, or in order to set the overflow bits, you need to use special addition or subtraction with with s at the end, or in other, it is a set. This this instruction is add and set, add with immediate and set, subtraction and set, and subtraction with immediate and set. And so this instruction, after doing the addition or subtraction, will set the flag by this overflow bits, so you can know whether the result is over the range of your bit set, or we need be overflow will show you whether it over your range. And so you have 4 condition codes set by the operation. You can set if it is a negative value. If you look in, for example, here you look into this value, this bit will be if this bit equal to 1, the most significant bit equal to 1, it implies that this value will be a negative value. You will have another condition, that is set if the result is 0, set if the result is overflow, and here is what we care now, and set if the carry is occur, or in other words, if you add 2 values together and the result get over the range of bits you use, a carry will be. And here is how you show the components for that operations in CPU of add, sub, and OR. It called arithmetic logic unit, or ALU. In a simple manner, you can see it here. An one bit ALU will have 2 bits input, one each for each of the operands, and 1 bit outputs. These 2 bits can be add or can be sub and OR, and given the result out here. Next, we will go to binary multiplication. The manner we do binary multiplication are completely the same with what you do with decimal number. Here is an example. If you have a multiplicand of value of 8 or 1, 0, 0, 0, and you want to multiply with multiplier equal to 9 in decimal, or 1, 0, 0, 1. And please remember that here in our example, we don't care whether this is a negative or positive number, and so it means that these values are positive value. And so if we do the multiplication, we will take the first bit or bit 0 of the multiplier. We multiply with the multiplicand. So 1 multiply with 1, 0, 0, 0, and we have 1, 0, 0, 0 as result. And then the second bit 0 multiply with this, we will have all 0, but these values are shift 1 bit to the left, and then the third value of 0 here multiply with this, we all 0 and shift one more time to the left, and finally this bit of 1 multiply with 1000 will be 1000, and this value again being shift one more bit to the left, and so we add finally we add all these columns together, and here you will have the result of 1001000, and we use 8-bit value, 8-bit data, because we will consider this as a positive value, so this bit, hidden bit, will be 0, or this bit you can see in our multiplication, but it will be 0 to imply that this is a positive value, and so this positive value will equal to 72 in decimal, and it is the result of 8 by 9. About the multiplication algorithm for binary, we can see here is the algorithm. I will zoom it out for you. At the start point, you will get two values into our algorithm. You will test the first bit or bit 0 of the multiplier. If that bit equal to 1, it means that you need to add the multiplicand to the product and place the result in product register. If this value is 0, here, if the result is 1, this case, you will need to add the multiplicand to the product. If it is 0, this case, you will add nothing to the product. So here you if it is 0, you add nothing to the product, and for the product, and then you need to shift the multiplicand register left for 1 bit, and after that you shift the multiplier register to the right for 1 bit, and you check whether you get to the final repetition. If you have 4 bits, it will be 4. If you have 64 bits, the number of repetition or number of loops you have to do, that is 64, and if you already get to the final repetition, your algorithm has done, and the result will be available in your product register. Detail of this, in more detail of this, you can see in our lab or in your lecture. For the multiplication hardware, this is the multiplication hardware for 64 bits multiplicand. You will have a register here for multiplicand. This register we need to shift 1 bit to the left after each of each iteration. The multiplier register is here, and it will need to shift to the right for 1 bit after each iteration. And here it is an ALU with 64 bits, and you can add the result of multiplicand with the product, and product here, it come back here, so we will have the product together with multiplicand after shifting, and then you add it here and you write it back to the product register. The multiplier here, the least significant bits of multiplier will be used in control here to decide whether you will add product with multiplicand or not, or you will give the product as it is back to the product register. For binary division, of course, it will work. We will do it as you do in division of decimal numbers. Here is an example. You have a divide n here, and you have divisor here. You will take the divide n is 1 0 0 1 0 0 0, and the divisor is 1 0 0 0. And so you do the same with we do it with decimal number. You will take the most significant 4 bits here, because here the divisor is 4 bits. So you take the most significant 4 bits of the divide n here, 1 0 0 1, and you minus for the divisor here. So minus 1 0 0 0, and the result for this subtraction is 0 0 0 1. And then the next step, you take this bit, the next bit or bit 0 1 2 or bit 2 from the divide n down here, and then you subtract for divisor 1 0 0 0 here. This arrow implies that you shift this 1 0 0 0 value 1 bit to the right, so you align it here. You will take 0 0 1 0 minus 1 0 0 0. You can't do it, so because the remainder here is smaller than divisor, so the result or the next bit equation will be 0 here. Similarly, you do with this bit 0, you add it here, but the result is still 0, and the final 0 bit will be here with this shift up to here. So you will have the remainder 1 0 0 0 equal to the divisor. So the result for this equation bit will be 1, and the remainder will be 0. And so you can see that here 72. Again, we consider this as a positive value. Divide for 8, you will have a value of 9 here. And about the division algorithm, you will at the start point, you prepare the equation as 0, and you need to subtract the divisor register from the remainder register and place the result in the remainder register, and then you test the remainder. If the remainder is smaller than 0, which implies by the most significant bits of the remainder, in that case you need to here, if the remainder is smaller than 0, implied by the most significant bit of the remainder, you need to restore to the original value of the divisor by adding the remainder with the by adding it with the divisor, and then you also need to shift the equation register 1 bit to the left with the least significant bits of equation setting to 0. If the remainder is larger than 0, larger than or equal to 0, which implies by the most significant bits equal to 0, in that case you shift the equation register 1 bit to the left with the setting of the new most less significant bits or the rightmost bit of the equation to 1. And after that you have you will need to shift the divisor register to the right for 1 bit, and then you check whether you get to the final repetition or final iteration or not. However, in division algorithm, the number of iteration will be the number of bits for the divisor adding with 1. So if you have 64 bits divisor, you will need 65 time of iteration, and the 65th repetition will be used to confirm the it will be used to confirm the most significant bits of the region or the side bits. Here is the simple binary division hardware. You have the divisor available here as 64 bits. The equation will be here as the 32 bits, because if you make 34 if you take because if you divide 64 bits to 64 bits value, you will have half of the bit number, that is 32 bits region. And so the remainder here, you will initialize it by the division divide, and here you can see that you take the remainder and you subtract for the divisor each time, and the result will be written back into the remainder here. And you also need to check the most significant bit of the remainder. If that bit is 0, you will push 1 0 into here, into the right of the equation, and then shift everything 1 bit to the left. If the result or the most significant bits of the remainder is 0, which implies that the remainder is a positive value, you will shift 1 into the equation to from the right. And at the same time, you need to shift the divisor 1 bit to the right, and you do the same here until you get the final iteration. The improved for this binary division hardware and the improved for the binary multiplication hardware can be seen in our lab, and you can refer to the video on that for the improved hardware. And here we will go to the floating point. You know that if we just simply show our value by 64 bits, we can get to 2 power 64, and we can't have the fraction value. That's why we need a floating point in order to make the result, in order to be able to store a larger value, and also in order to have the fraction value. So here is the structure of a floating point value of a floating point value. You will have the first bit here. The most significant bit is the side bit. If this side bit is 1, it will be a negative value. If it is 1, if it is 0, it will be a positive value. And then the exponent and the fraction. The value of this format will be -1 power s. So here will be the sign for the value x, and then multiply with the significant, which is 1 plus the fraction, and then multiply with 2 power exponent minus bias, why we need to what is the bias? Here we know that we will have the fraction of the exponent of positive or negative value in order to show the floating point, and so you need to take the original exponent and minus to bias here. So here it is explained for what I already say. The S is the sign bit. 0 means non-negative and 1 means negative value. In order to normalize the significance, we can see here 1 is smaller or equal with the significance and smaller than 2. So here you can see that significance will range from 1 point something to very close to 2, but it is still 1 point something, which implies that this 1 point bit can be removed. And so we remove this bit 1 here, and we just keep the fraction after this one. So 1 point something here, that something will be kept in fraction, and this bit for 1 will be removed. And when we do calculation with floating point, we will need to add this one together with the value of fraction to revert it back. And saying about the exponent, we will have the bias here, and as you can see here, we have two types of floating point: single precision or double precision. For single precision, we will have 8 bits for exponent and 23 bits for fraction. For double precision, the number of bits for exponent will be 11, and the double of bits for fraction will be 52. And the bias for the single precision will be 127. And the bias for the fraction for the exponent of the double precision will be 1023. Why it is 127 and 1023? As you can see here, if we use 8 bit for the exponent, you can in binary you can show a value from minus 128 to 127 because for 8 bit we will have totally 256 value, and for 11 bits we also be able to show the value from minus 1024 to plus 1023, and totally with 11 bits you can show 2048 values here. So here again you can see single precision with 32 bits in total, 1 bit for sign, 8 bits for exponent, and 23 bits for significance here. And how you can calculate this value? It will be minus 1 power sign multiplied with 1 plus fraction. As we say before, this bit 1 is a hidden bit, and so we need to add it with the fraction for the significance, and then we multiply it with 2 power the exponent minus 127. And for the double precision, we have the same thing, except that it uses totally 64 bits with 1 bit for the sign, 11 bits for exponent, and 52 bits for the fraction or the significant. And how you calculate it will be shown here. Similar with other number representation, Of course, a floating point will have some limitation in the value it can represent. Depends on the number of bits it has. As you can see here, in this part, the significant, it has the value of 1 plus with fraction, and it may imply that the value will always be bigger than 1, and then it multiply with 2 exponent something, and so it means that the value of floating point cannot get to 0. It can get very, very close to 0, but it can't get to 0. And also for the biggest significant and the biggest exponent it can have, it also have the upper limit that it can show, and here is the overflow and underflow of floating point. For the single precision number, the biggest number that the floating point can be represented is 2 minus 2 power minus 23 multiplied with 2 power 127, and the smallest number in negative sign, it is minus 2 power minus 23 by 2 power 127. Similarly, for the double precision number format, that value will be this. The biggest one is the 2 minus 2 power minus 52 by 2 power 1023, and the smallest number in negative sign, it is minus 2 minus 2 power 52 by 2 power 1023. So this is the biggest number in positive, and this is the smallest number in negative. That the single precision and double precision can be shown, can be represented, and they are called positive overflow and negative overflow. Besides that, as we said before about the value of the significant, which is bigger than 1 and multiply with 2 power something, so this part, the absolute value of this part will get close to 0 with the smallest exponent, but it can't be equal to 0. And so there is one more thing that related to floating point, format, that is the underflow, in which we also have the positive underflow and negative underflow, in which the positive underflow for single precision is 2 power minus 126, and negative underflow for that, it is minus 2 power minus 126. And if we use the double precision number, the underflow will be 2 power minus 1022, and the negative underflow will be minus 2 power minus 1022. Well, now we will go into floating point addition. Here we will look into a decimal example so you can easily understand how floating point addition occur before we go into the algorithm. In fact, the decimal addition with floating point will occur in the same manner with the binary one. So we take the decimal here. Here we have two operands, 9.999 by 10 power 1 plus 1.610 by 10 power minus 1. If you look into this, you can see that here both of them start with a digit, and then the fraction follow by this. So 9 point something, and here 1 point something. And this part, it is the exponent 1 here and minus 1 here. So if we look into the format, into this format, you can see that, well, it has the same format with the single precision and double precision, which will be 1 plus with fraction and by 2 power something. Each operand, of course, depends on their value. The fraction will be different and the exponent also be different. And for that reason, we have here the exponent of 1 here and minus 1 here. So if we want to add these two values together, of course, we need the exponent as the same before we can add them before we can add the significant together. So at first we need to align the decimal point so that the two operands would have the same exponent. By shifting the number with smaller exponent, so here this number has the smaller exponent, and so we will shift this part, the significant, to the right together with adding the exponent by 1 by 1, and so we will have this shift to the right one time. We will have 0.161, and this exponent change from minus 1 to 0, and then we shift this one more time to the right, and we have the exponent change from 0 to 1, and so the new number of this will be 0.016 by 10 power 1. Now we can see that both of the two operands have the same exponent, and so now we can add the significant together. So we add the significant together, and we have the new value of the this addition, that is a 10.015 by 10 power 1. If you look into this value, you can see it has 2 digits at the beginning, so it is out of the format. That is a 1 digit and then point something. So we will need to normalize the region and check for over and underflow. We do that by shifting this value to the right together with adding one more to this exponent, and so we have the new value of 1.0015 by 10 power 2. And now we have this is the correct format for the floating point, but whether this value can be shown by the significant or not, we have to check it, and then we need to round and renormalize the value if necessary, and so here we round it to 1.002, and the exponent are keep the same. Here is the algorithm for the addition of floating points. We need to compare the exponents of the two numbers or the two operands. We will shift the small number to the right until its exponent match with the larger exponent, the same way we did before. After that, we add the significant parts together. After that, we need to normalize the sum either by shifting to the right and incrementing the exponent of the region, or we shift the region to the left and decrease the exponent. And then we need to check whether the overflow or underflow occur or not. If the underflow or overflow occur, we will need to give an exception which shows that the value can't be, the region can't be shown by the current precision floating point. If the overflow or underflow didn't occur, which means that our region can be stored in the current precision format, we need to route the significant to the appropriate number of bits, and then everything will be done. And we need to check if we still need more normalization or not, and if it's done, everything is okay, the algorithm go to done. Here is how we do the multiplication for floating point. Again, we consider the same this value in decimal and multiply together. 1.110 by 10 power 10 multiply with 9.2 multiply with 10 power minus 5. Here is the multiplication, so the algorithm is less complex in comparison with the addition for floating point, because we can simply add the exponent together to have the new exponent, and so we add the exponent together. So here 10 8 minus 5, and we will have the new exponent of 5. And then we multiply the significant 1.11 multiply with 9.2, and the result will be 10.212, and so the final result will be 10.212 by 10 power 5. And then we will need to normalize and check the overflow or underflow occur, so that we can guarantee that this significant will have the format of 1 point something, and so we shift this value 1 bit to the right and increase this exponent to 1. We have 1 point something by 10 power 6. And then we need to round and renormalize if necessary, and so here rounding we make 1.021 and multiply with 10 power 6, and of course we need to determine the sign of the result, and the sign here will be added by plus or minus. It depends on the size of the two operands, in two input operands. So here is the algorithm for floating point multiplication. At first we will add the bias exponent of the two numbers, and subtracting the bias from the sum to get the new bias exponent. And then we multiply the significant. After that we normalize the product if necessary, and shifting the result to the right and increase the exponent to make sure that the significant has the format of 1 point something. And then we need to check the overflow or underflow if they occur. And if it occurs, the exception need to be given, and if not, we will route the significant to the appropriate number of bits, and then if we need to normalize again, we will do it. If not, we will give the we will set the sign for the result. And then everything is done. And of course, for setting the sign of the result, you know that if one positive number multiply with one negative number, you have negative number. If two positive operands multiply together, or two negative operands multiply together, will give the positive result, and so we can use that condition to set the size bit, and after we have the final result available. Yeah, thank you very much, and this is the end of the summarized lecture about arithmetic in computer.